So, hello friends. Today we're going to be learning about what Kahn's algorithm is. Basically, Kahn's algorithm is used to find the topological sort of any graph. And what do you mean by topological sort? So, let's say we have this graph, right? So, a topological sort is basically a sequence of a linear sequence of order or linear sequence or ordering of nodes such that if U comes before V, that simply means that even in the graph also, U appeared before Z. Like, let's say one of the possible topological sorts for this graph can be if 2 and 4 is here. So 2 and 4 has to occur on the on the right side of 1, because in the graph also it appeared on the right side. And here also 3 and 5 appeared on the right side of 4 and 2 and 4. So it has to be like that way only. It has to be like that way only, that 3 has to occur on the right side of 2. Anywhere, it is not necessary that it has to be here. 5 would also come here, and then 3 would come. That would also be a possible topological sort. And 5 has to come here. So this is among one of the possible topological sorts for this graph. It is not the only one. There could be like 1, 4, 2, 3, 5. There could be another one with 2, 4, 5, 3. So there are a number of ways you can find out that there are a number of topological sorts for a given graph. But remember that topological sort is only can only be found for graphs that are acyclic and directed. And it also makes sense that you want the graph to be directed. Otherwise, what if something like this would be there? Which one would you call should be appearing first? Because if that next graph, this is moving towards itself, and this one is moving towards this. So there's no way we can figure out which one should come first. For a topological sort, we need a acyclic as well as directed. Why do we need acyclic? Acyclic means that it shouldn't be having a cycle. What if because if there would be like something like this, and for 3, which one would you call like appeared first? For 5, which one would you call like should be appearing first? Either 4 or 3 or both, right? But it doesn't make sense. It is not cyclic also. It is not cyclic. It is not cyclic so far, right? But what if there would be something like, it is not happening here. So let's say we add this. So this is acyclic. Okay. So for one, which way you would say, for 1 you would say like 3 must appear before 1. Okay. For 2 you would say 2 must appear after 1. Okay. And for at the same time you would say that 3 must appear after 2. Okay. Is there any way possible? Is there any such topological sort which you can find out considering these 3 situations? Is there any way? Like 3 must appear before 1 as per this what you can say edge. 1 must appear before 2 as per this edge, and 2 must appear before 3 as per this edge. So considering these 3 conditions, I don't think there is any topological sort available. You can try it on your own. You can try to find out which is there any linear ordering of nodes which can satisfy these 3 conditions. You will end up getting the result that there is no possibility. So it is very essential for us to know that topological sort can only be found out in a acyclic directed graph. So what are the ways to do it? There is one way via BFS, and there is another way via BFS, and the one which we use with BFS is generally known as Kahn's algorithm. Kahn's algorithm, if I'm not pronouncing it right, so bear with me. I don't know, it's not pronunciation, it's Kahn's algorithm, I guess. Kahn's, it's not Kahn, yeah, either. So I would be calling it Kahn's. So don't mind by the hells. Okay. So let's say we have this graph. So first of all, we need to ensure that this is acyclic and this is directed. So we can simply observe it and conclude that yes, it is acyclic because we are not having any cycle. And at the same time, it seems directed as well. So what are the steps to find out the concept? Well, I have pointed out all the steps here. So find out the degree of, so what are the steps? So first of all, we need to find out the in degrees of all the nodes in the graph and store it in a vector in degree. So what we'll be doing is we'll be finding out the in degrees. What do you mean by in degree? So let's suppose this is a node and this node is having these 3 edges coming towards it. So we can say the in degree of this node is 3. Okay, good enough, extend, good enough. Okay, so we will be trying to find the in degrees of all these nodes. So on finding, so we figure out that for 1 we are having an in degree of 0 because there is no node coming towards 1. For 2 we are having 1, that is from 1, and for 3 we are having 1 from 2, and for 4 we are having from 2, and for node 5th we are having it from 4. So the in degree that we wanted. Now what you want to do? On the next step, you want to find out all those nodes which are having an in degree of 0 and store them in a queue. It is a parable process, so bear with me. So I'll store them in a queue. So on iterating out that one is the only node here which is having its in degree as 0. So I'll store that in a queue. Now what you want? Now you want to run a while loop. As long as queue is not empty. And on each iteration of the while loop, what you want to do? You want to pop out the front. And put that in the topological sort vector. That is going to be our final answer. Okay. So we want to put that in our topological sort. We put it. And then we want to iterate through the neighbors of the node and decrease the in order of those neighbors by 1 because we have included that node already. Because we have included the front already, we can assume as if it is not the part of our graph anymore. So we want to decrease the in degrees of its neighbor by 1. And because our front is no more apart, it is already been taken. So there is no meaning of considering its in degree as a source to its other neighbors. So what we do is we pop out the front, we put that into a topological sort, and we decrease the in order of it. Not in order, it degrees. I'm so much using in order because I have done in degrees. So I want to decrease the in degrees of its neighbor by 1. It will take some time. So, okay. And on doing so, let's say for the first iteration, we had 1 in the queue. So we popped out 1. Now we put that into the topological sort. We put it. Okay. 1. So let's say we have 1 in just so far. Now I want to iterate just so far. Now I want to iterate through the neighbors. So I know that 1 had 2 as its neighbor. I scroll up. So 1 is having 2 as its neighbor. So what I would do is I decrease the in order of 2 by 1, so here it becomes 0, which it was 1 earlier, which so it becomes 0. Now repeating this process, and now we want to focus on the 4th one. After doing this, we want to focus on the 4th end. Like as we are decreasing the in degree of the neighbor, if we ever come across a situation that the in degree of our neighbor has become 0, so we want to put that into the queue. So here we find out that the degree of our neighbor, that is 2, has become 0. So we want to put that into the queue. So we will put that into the queue and our queue will become something like this. Okay. So now the front of our queue is 2. And so repeating this process as long as our while loop our queue is not empty. will give us a topological sort in our TS vector or DNF. So let me just code down it for you. So here's the question. We want to find out the topological sort for a directed acyclic graph with vertices V and edges E. So what we want? So first of all, let's declare a vector TS which will be storing our final topological sort. We also want a vector which will be storing our n degrees. And what else we wanted? We wanted a key. Sure. Now, before we... so what do I want to find out first of all? We have been given the adjacency, so we don't need to beat it into by ourselves. So now I want to do, what do I want to do? I want to find out the in degrees. So how can I do this? So let me just traverse, zero, because we are, if you see here, the nodes value are going to be from 0 to n minus 1. So we will be starting off with 0. Doing so. Now what do I want? I want to traverse in the neighbors. And I want the increment, that in degree of our neighbor has become 0. I want to push that into our queue. So I push it. So I simply push it. And just return out of original sort. So this is the entire code for finding out our topological sort. Well, let me just try to run this, just have a look. Is everything fine or not? So let me just try to run it. Segmentation fault. So where are we adding wrong? The value is coming. Okay, so I had to initialize the size of in degree, because if we are doing something like this, then we first have to make sure that we have given in degree the space of 3, because if you are doing something like this, we have to do it. That's what C++ does. That's how C++ works. So let me just do it now. Do I get the right answer? Yes. Yes, I did. Let's try to submit it. This it gets submitted. So this was the code for our topological sort. I hope that you could understand. And if you find my understanding a bit confusing, so bear with me. I'm just new to the YouTube space and I'm new to teaching as well. So I will try to